I'm going to go over one example of each type of factoring, so if you had any questions on it, you could jump just straight to the one that you normally have trouble with. For the first example, greatest common factor, that's what you should always be looking for. So for the first example between 2x and 6x, both 2 and 6 are divisible by 2, and they both have one x in common. So if I factor that out, I would just be left with an x and a plus 3. I could check that I factored that correctly by redistributing in and making sure I get that 2x squared plus 6x. For the second example, it's still a GCF, but notice that the greatest common factor is a binomial in both of these instances. That there's a 2x minus 5 I can factor out. And I'm multiplying that 2x minus 5 to x plus 7, then a plus sign. And I'm also being multiplied to 5x plus 2. Now, it looks like I've got some like terms I can combine in that second set of parentheses. 5x plus 1x would just be 6x, and 7 plus 2 is 9. So I've factored out that GCF of 2x minus 5, and I've actually created this issue where now in that second set of parentheses I've got a GCF of 3 that I could pull out. So for my final answer, I'm just going to pull the 3 out on the outside. Remember, it's multiplication, so it doesn't matter what order I multiply these factors in. And a 2x plus 3. So that's what a fully factored form would look like, even if the GCF is 2x minus 5. Example 2, a difference of two squares. Remember that if you've got something squared minus something else squared, that factors into the first something plus the second something times the first something minus the second something. So in this instance, 2x would be what I have to square to get 4x squared, and 5 would be what I have to square to get 25. So 4x squared minus 25 would factor into 2x plus 5 times 2x minus 5. And the same rules apply if the exponents are higher. Let's say that's 2x to the 4th instead of squared. I would just have to square 2x squared rather than just 2x. Number 3, a trinomial with a leading coefficient of 1. This was also from the first lesson. You simply ask yourself what numbers add to negative 5 and multiply to negative 6. Well, if you think of factors of negative 6, there's really only a couple, right? There's negative 6 and 1, and really 2 and negative 3. But for negative 6 and 1, if I make the 1 negative, I could add them and get positive 5. So I'm going to use that as my winning pair, rewrite it as x plus 6 times x minus 1. Of course, you could always double distribute, multiply the x to the x to the minus 1, 6 to the x, and 6 to the negative 1. And when you simplify, you should end up back with what you started with. So when you're on a test or something, that would always be a good way to check. Number 4, factor by grouping with 4 terms. As long as it's in standard form, maybe you need to rewrite it first, you can group the first 2 terms and the second 2 terms. So between the first 2 terms, I could pull out an 2x squared as a GCF, and I would just be left with x to the first minus 2. And again, if I distribute that back in, I'd get the same thing. And I could pull out a 5 from the second 2 terms and also be left with an x minus 2. Now this should be the case every time that there's a greatest common factor of x minus 2 between these. So I could rewrite it once on the outside, and I'm left with 2x squared plus 5. I checked real quick, there's nothing I could do to factor 2x squared plus 5, so this is as far as I could go. I could also do grouping with 6 terms. Now there's 2 different cases. In this first case, I'm going to group every 2 terms. I know that because I'm looking at the order of the exponents. I want to see when it stops decreasing. So it goes from 4 to 3, then back up from 3 to 1, then back up from 2 to 0. So wherever your exponents stop decreasing, that's where you stop your grouping. So for these first 2, I could pull out an x squared be left with x squared minus 1. For the next two, I could pull out an 11x, and again be left with x squared minus 1. That should always be the case that those parentheses match. I could pull out a 30, and again be left with x squared minus 1. So there's still a GCF of x squared minus 1 between all my terms here. So I can factor that out, and I'd be left with an x squared plus 11x plus 30. But wait 1 minute, there's a little bit more factoring that we could do. This to me looks like a difference of two squares, and that trinomial has a leading coefficient of 1, so I could factor that like normal. So this dots becomes x plus 1 times x minus 1, and that trinomial, I could just think of numbers that multiply to 30 that add to positive 11. That would just be 6 and 5. In some cases, though, I have to group in groups of 3. And again, if I look at the order of the exponents, they go from 4 to 3 back down to 2. Then it stops decreasing and goes 2, 1, 0. So that's the clue that tells me to group it in 3s instead. There will never be an instance where you need to rewrite the terms, though, with 6 of them. So let's say I pull out an x squared for the first 3. I'd be left with x squared plus 15x plus 54. And the only thing I could think to pull out from these 3 terms is a minus 1, and that will change all of the signs so that my greatest common factor between these now is this nice trinomial, x squared plus 15x plus 54. So I could pull that out, and I'm left with x squared minus 1 again. Again, this second set of parentheses is just a difference of two squares. And the first set is a trinomial with a leading coefficient of 1. You need to think of numbers that multiply to 54, but add to 15. Now I know off the top of my head what they are, but if you weren't sure, you could always go into your calculator. And I'm going to go into y equals. And I'm looking for factors of 54, so I'm going to type in 54 divided by x. I'll hit the second button, that blue button, and graph, and it'll bring me to a table. And these are all of the pairs of numbers that multiply to 54. 1 and 54, 2 and 27, 3 and 18, 4 and 13.5, and so on and so forth. The winning pair for me is 6 and 9, because if I add those together, I get 15. So in a pinch, if you can't find the factors, you could always use your calculator to help you there. To factor a trinomial with a leading coefficient that isn't 1, we've got to use the AC method. So I start by multiplying the 2 and the 5 to get 10. And I want to think of numbers that multiply to 10, but add to positive 11. So it looks like 10 and 1 would fit pretty well there. Then I'm going to split that 11x up into just a 1x and a 10x. So I'm using those numbers there as the coefficients. So 1x plus 10x is the same thing as 11x. I didn't change the value. I'm only making this 4 terms so that I could use grouping to finish it off. Now, you could swap the order of those and the factoring would still work out. You would just get your factors in a different order. But remember, multiplication is commutative, so it doesn't matter what order you write your factors in. I could factor out an x from the first pair and a 5 from the second pair. They both have a 2x plus 1, and we'd be left with x plus 5. For a sum or difference of cubes, there's 2 formulas you got to know here. I recognize sum or difference of cubes as 2 terms where both of the numbers are perfect cubes. So x cubed is just x cubed, but 64 is 4 raised to the 3rd power. Again, if you didn't recognize that as a perfect cube, you could always go into your calculator, type in x, little caret to get the exponent, and then 3, so that's x cubed there. And if you go to your table again, you get all the perfect cubes. So 1 cubed is 1, 2 cubed is 8, and so on and so forth. So the formula for a difference of cubes is if I'm subtracting two things cubed, that factors into the first thing minus the second thing times the first thing squared plus the first thing times the second thing plus the second thing squared. And the sum formula looks pretty similar. It's a cubed plus b cubed equals a plus b times a squared minus ab plus b squared. Now there's a reason why I call these SOAP problems. If you notice, for the difference, I started with the subtraction sign, and the first sign I saw was the same. The second one was opposite of what I started with, but the last one is always positive. That works for addition as well. The first sign is the same as what I started with, addition. The next sign is opposite, and the last sign is always positive. So that's an acronym that might help you remember these, but at the end of the day, it's just going to be memorization. So in this case, my a could be x and my b could be 4. So when I substitute in x minus 4 times x squared plus 4 times x plus 4 squared, which would just be 16. And you'll never be able to factor further with a sum or difference of cubes. So even though that's a nice trinomial, it will never be factorable. So at least these will just be one step. Sometimes you'll have coefficients out in front too. It's not a huge problem. But I think to myself, what would I cube to get 27? Would just be 3. So I'd have to cube 3x to get 27x cubed. And 125 is a perfect cubed as well. That's just 5 cubed. Again, you could check in your calculator if you don't have those memorized. This is a sum of cubes, so I'm going to use that bottom formula now. The first thing plus the second thing times the first thing squared minus the first thing times the second thing plus the second thing squared. But if I simplify this a little bit, when I square 3x, 3 times 3 is 9, and x times x is x squared. 3 times 5 is 15, so I could just make that 15x, and plus 25. So that would be what my final simplified answer looks like for factoring a sum of cubes. The last kind of factoring is if I need to do it via substitution, in that I notice that there's this x squared minus 6x in 2, but not all 3 of the parts of this expression here. So I'm going to make a substitution. I'm going to say let a equal x squared minus 6x. So everywhere I see an x squared minus 6x, I'm going to replace it with a. So that first term is just a squared, a times itself. The second term would be 13 times a, and plus a 40 at the end there. Well, now this just looks like regular factoring, where I could ask myself what numbers add to 13 and multiply to 40. I'm using an a here instead of x because that's the variable that I chose. You can pick any letter, really. And numbers that multiply to 40 but add to 13 would be 5 and 8. Now that we've factored by making the substitution, I'm going to plug that x squared minus 6x back in for each of those a's. So that first set of parentheses will become x squared minus 6x, then plus 8. And the second set's going to be x squared minus 6x plus 5. But I'm still not done factoring. It looks like both of these are going to be AM method because their leading coefficient's 1. So I could ask myself what adds to negative 6 and multiplies to positive 8. That would just be a minus 4 and a minus 2. Remember, a negative times a negative is positive. And if I want numbers that add to negative 6 but multiply to positive 5, well, the same rule applies. Negative 5 and negative 1. So this is what a fully factored form would look like as a product of 4 linear factors.